Hello friends, welcome to the Vidyalankar. Myself, Professor Hari Soja, today will be discussing very basic topic in digital electronic called logic gates. This topic is very important in order to understand digital electronic circuits. Now, all of us are using digital equipment these days. Every machine is a digital electronic machine. So, we'll look into what is the basic building block for these digital equipments or circuits. Answer will be logic gates or simply gates. Now, here we'll discuss this operation with the help of basic network. Here I have taken LED connected to a battery, and in between I have two switches, switch A and switch B. Both of them are connected in series. Now, in order to have light from LED, both A and B need to be closed. So, in binary or in digital circuit, if I represent open position by 0 and closed position by 1, I can say this L, that is a light from LED, can be written as A, means B. So a digital circuit or digital symbol equivalent to this network is your NAND gate. So this is the symbol for NAND gate. You have two inputs A, B, and output is A into B. Now there are two inputs A and B. So you can have four combinations of input, that is 0, 0, both of them can be 0, 0, 1, 1, 0, 1, 1. And this is the output for each combination. This table is known as truth table in digital circuits. Now, if you look at this if you look at this truth table, you can see output is 1 for only one combination of input out of 4 combinations. So that's why output of AND gate is known as mean term or minimum term. If you compare this or in contrast to this circuit, if I connect switch A and B like this in parallel, then I'll get a light from LED whenever A or B is closed. So this is A plus B or A or B. Digital circuit equivalent to this configuration is your OR gate. So AB output is A plus B. Again truth table. Here you can say when both of them are open, output is 0. Otherwise you will have a output. And out of 4 combination of inputs, 3 gives you output as 1. So it is known as max term or maximum term. If I combine this in digital electronic, we need a larger circuit. This is a very basic building block. So actual circuit will be quite large. So just one example where we combine both of these operations AND and OR. So what I have done is A and B are in series, means AND operation. C and D are in series, again AND operation. Both of them are in parallel, means OR operation. So my expression for getting a light from LED will be AB or CD. So AB plus indicates OR, C into D. This kind of representation of Boolean expression is known as SOP, sum of product. A into B product, C into D product, add them, sum of product, SOP representation. Now this SOP representation can be realized by using digital or a gate level design. So you will have one gate for getting A into B. If you look at this will give you A into B, this will give you C into D, and this will give you the Y, AB plus CD. One more example, OR AND. So So here I have just changed the position of switches. A and B are in parallel, C and D are in parallel, and both of the configuration or both the networks are in series with each other. So my expression will be L, or you can say L here. L is equal to get a light, you will have expression A plus B, C plus D, and multiplication. This arrangement is known as POS, product of sum. First get a sum A plus B, sum C plus D, sum, and then product of them. Again, this can be realized by using gate network. So here I'll get A plus B, and here I'll get C plus D. A plus B, C plus D, and then multiply them to get the equation. This is how you realize the digital expression, or we call them as a Boolean expression for digital network using gate circuits. Now, these are two basic gates. One is AND gate, other one is OR gate. There are few more gates. So first one is a NOT gate or an inverter gate. Very simple circuit which gives you output as a complement of input. So if input is 1, output will be 0, and 0 will give you 1 at the output. Just inverter, complement. And then NAND gate. NAND, as the name suggests, AND plus NOT. So this is my AND gate. Output of AND is input to the NOT. So entire combination is known as NAND gate. So this is your NAND gate. Last one is this resulting configuration is your NAND gate. Now if I draw the truth table, see AB, this part is same as AND gate, just inverted. So it was 0, 0, 0, so 1, 1, 0. Complement of this. Similar way, I can have NOR gate, that is OR plus NOT will give me NOT. So this is my symbol of NOR gate. See the bubble at the end. This bubble indicates NOT gate. NOR means AND plus NOT. This bubble indicates NOT gate for both the circuit. And this is the truth table. Again, you can see this truth table is complemented or inverted from here. This is OR, just inverted. 0 will become 1, 1 will become 0, and so on. Apart from these gates, there are two more gates which are known as a special purpose gate or exclusive gate. Before discussing those two gates, let's classify these 5. Out of these 5 gates, NAND and NOR are known as universal gate. NAND, NOR gate are known as universal gate, and other 3, NOT, AND, and OR are known as basic gates. And let's first let's discuss exclusive gates or XOR and XNOR gate. So first in that is XOR gate, exclusive OR. So exclusive OR is like this. 2 inputs again and 1 output Y, and XOR is represented like this. This symbol indicates XOR. Actual expression for this is A bar B and B bar. Let's see the truth table. Truth table, you can say inputs. 2 input again will give you 4 configurations or 4 combination, I should say. 4 combination, and for each combination you have to list the output. So here this is your exclusive OR. You can see output is 1 when inputs are dissimilar. When same inputs are there, output is 0. We'll discuss application of this. And if I add a NOT gate to this, what I get is X NOR gate. So X NOR will be, this bubble indicates the NOT at the output, A, B, Y, and A X NOR B. This is the representation for X NOR, and actual output will be AB plus A bar B bar. And truth table, no need to draw truth table again. If you add, if you take a Y bar here, Y bar, that is 1, 0, 0, 1, this will be truth table for X NOR. This is X NOR, this is X NOR. So these are basic gates in digital electronics. Now let's discuss one example where these XOR and XNOR gates can be used in digital circuit. For example, if you have to design a logic circuit to allow a signal from input to output under certain condition. The condition is when both the control signals. Let's discuss that. You have a logic circuit. You have one logic circuit. This is your logic circuit, which you have to design. It has, let's say, X. This is the input. Y, which is the output. And you have two signals, A and B, which are the control signals. Okay, so this circuit you have to design. Condition is that Y is equal to X if A is equal to B equal to 1. That is, our input is transferred to output when both the control signals are 1. In this case, you can see input, this is X, will reach the output if X OR condition is matched. So A is 1, B is 1. So in this case, you can simply use A, B, X OR them. Right? X OR them, and then this is your input X. Give this X input, and let's say this is my output. Now let's understand this. Okay, so if this is 1, this is 1, then one day you will get a 1. If this is 1, this is 1, you will get a 0 here. 0 means at this point you will get 0, and then this is OR gate. So X will be transferred to Y. Thank you.